When did you first meet Fan Chung?
So Bell Labs is in Murray Hill, New Jersey, and not far away from the University of Pennsylvania, like an hour and a half away. And I knew her advisor at that time, Herb Wilf, and I would give talks at UPenn, and he said, I've got this terrific student working in Ramsey theory. Well, that's pretty natural. And I met her, and she came, gave a talk at Bell Labs, impressed everybody, so we made an offer, and she took it, and she was hired, and there she was, Bell Labs. So, we've written, she's a great collaborator, and, super strong. And we've written, I think, 90 or 100 papers maybe, and now she's kind of gone off into spectrograph theory, which is an area I don't work in so much, but it's just part of the collaborative activity at the labs where people would just work with each other in joint papers with, a tremendous number of people. I mean, Ligarius, Lisco, all these people, Gary, Johnson.
What other collaborators stand out in your mind from your career?
I've had a lot. I mean, I have papers with John Reardon. I mean, kind of a legend in combinatorics, right? And of course, with Erdős, we have 25 or 30 papers, something like that. He was a key player. Percy, you probably have 15 or 20 papers. And it's just that typically you solve a problem, but it's not completely solved. There's always a little more to do in the next case. And what about 3 dimensions? And what about hypergraphs? And what about the directed case? And so forth. And so, each solution generates 3 new problems typically, so you don't run out. And it's just that at the labs, that environment, you get exposed to so many different kinds of problems. Extremal graph theory problems and geometrical packing problems. Problem with Erdős we just worked on again recently. You take a square of side alpha and you want to pack as many unit squares that don't overlap as possible. How many can you get in? Well, if alpha is an integer, like 1,000, then you can have 1,000 squared, 1,000 by 1,000. But suppose alpha is, say, 1,000 plus 1 over 100, just a little bit more. Well, if you pack them in a nice orthogonal way, it's pretty good. You have a little waste area around the outside that's proportional to 1,000, proportional to alpha. So you wasted kind of a linear amount. Turns out by putting them in crazy angles, you can actually get the waste down to about alpha to the 7/11ths, about point, much better. And now is that the best? And now with a little more work, you can get it down and down. And then Roth and Von showed that you can't get it better than the square root of alpha. So what's the right answer? I don't think it's the square root, by the way. I think it's bigger. But so just little problems like that lead to kind of, harder and harder challenges. And, as is said, problems worthy of attack prove their worth by fighting back. That's my variation of the Pete Hine classic, yeah.